For the acceleration of any box given
On a frictional ceramic.
on Earth, on a frictional ceramic.
Yeah, there's a lot of extra caveats in there.
Without air resistance.
So if you have it on a 30-degree angle, then the acceleration will be 4.9 meters per second squared.
Cool.
Lots of RAM.
Box on right.
Of course, we can make it more complicated.
No.
Questions here? All right, so we're going to do a very similar problem to what we just did,
Oh no.
except we're going to get rid of that.
Oh no.
So let's talk a little bit about friction. We're going to add friction to the problem.
You.
So don't need, we'll just recreate that. There are two major models of friction. There's what I call the traditional one is what I call the Nook and Cranny model.
Okay.
Cranny. So, if I have a book on a surface, those who want somewhat of a real-life demonstration. There we go. Book on a surface. It's stopped because of friction, because we know that there has to be some net force acting on it.
Yes.
Because it did accelerate, it stopped, the velocity changed, and therefore there had to be a net force acting on it. Under the Nook and Cranny model, if we zoom in on a particular area there, we have the two surfaces. So we have the table, which on the microscopic level has all sorts of little nooks and crannies. And then the book,
Has its own nooks and crannies.
yep. And it's sort of like interlocking puzzle pieces. So you have the two pieces like this, and you know, it takes effort in order to get it, to break it free.
They break.
Once you break free, it becomes a little bit simpler to move. So under this model, you actually have two different types of friction. There's static friction, and then there's kinetic friction. So static friction and kinetic friction, well, they both depend on two major things. This was established, this formula actually found out, they first came up with in the late 1700s, and it really has not changed. Not significantly. The two things it depends upon are the surfaces and the normal force. The normal force determines how tightly they're pressed together. So small normal force, they might be like this. As you increase the normal force, they become more interlocked, and it becomes harder to get them to move. Static friction, as the name implies, this is the friction when it's not moving. The kinetic friction is friction when it is moving. Miguel, you seemed a little bit focused on the phone right there. Can you put it away?
Yeah, sorry.
The surfaces are brought into the coefficient. And so we'll have a use of S or a use of K, depending upon if it's static or kinetic. So the formula for kinetic friction, UK times the normal force. Static friction, on the other hand, so from our point of view, is this table accelerating?
It is not.
All right. I'm now pushing on it. Is it accelerating now?
It is.
No.
Is it?
Well,
No.
It didn't look like it.
Is it? I saw it. It moved.
Oh, but it shakes some. But are the feet moving?
No.
All right. But I'm applying a force on it that direction.
Yes.
So there must be some friction acting back that way to keep the acceleration zero.
Yeah.
I apply more force. What happens to the friction is I apply more force.
It applies.
Same friction. Same friction.
It should be more friction. If
Yeah.
I'm applying more force, it has to have more friction in order to match me.
Oh, right.
Yeah. It will do that up until a breaking point.
Static friction.
And so static friction is less than or equal to USY. Mu S times the normal force will establish the breaking point. And once you hit the breaking point, it's moving, and so suddenly there's kinetic friction. So if I plotted applied force versus friction, the friction should match the applied force up till I hit the breaking point. So this would be mu SY, that's the maximum static. And then once I hit that, it's all kinetic. This would be mu K1. That's the model for the Nook and Cranny model. That's what I was taught in high school. That's what pretty much every physics textbook will have. I know there's a group at NC State trying to get into more detail on this, actually trying to see if they can modify the equation at all. And it's the probology, that's it.
What?
From the Greek word for rubbing.
Okay.
The other model, called the attraction model. If we zoom in on that, what happens is, if we zoom in, that the nooks and crannies really don't make any difference, but you basically have these atoms really close to each other, and they are attracted to each other. The greater the normal force, the closer they are, the greater the attraction. So instead of repulsion, instead of one object trying to prevent the other one from moving across it, they're trying to get closer together. Under this model, there is no differentiation between mu sub S and mu sub K. And so the friction is less than or equal to uy. So if it's not moving, the friction will start increasing until it's the breaking point. Under this model, if I do the applied force versus the friction force, it'll look like that, where this is uy. It seems like very clearly you have two different predictions based upon what friction is really happening, what's happening with the friction. And yet, they haven't really, the jury's still out. I've met some physicists who still go by that, and some who basically insist that this is correct. I think ultimately the issue is, physicists for the most part don't deal with friction. That's an engineering thing. Engineers have something that works. They're very practical as a group. So why on earth would they want to bother going into any more detail, because they have something that works? And so we're stuck with a model that's been around for 300 plus years. I'm introducing this. At some point it might shift. If traditionist says anything, the American textbooks will change well after everyone else does. This is what your textbook does, and so this is what we're going to be using. Questions here? The textbook that we use for this class before the current one does spend a page on this one. They talk about that, they spend a page on this, and then they go back to that.
They say, you see this? Not gonna use it.
At least they spend a page as opposed to just a paragraph.
There's also this other model.
Something else.
We don't care. Just, okay.
All right. So, force diagrams, as we now have friction. Assume, for the sake of this, assume it will slide. In other words, I'm not worried about the static friction at the moment. We have weight acting down, we have normal force acting that way, and now we have one other force
Friction.
going which way?
Up the ring. Well, from the box up the ring.
Yeah, on the box up the ramp. We established we have the same I and J directions. Our acceleration does not change here. what do we need to break up? As we go down our list here. Force diagram done, acceleration done, coordinate axes done, decomposition. What do we need to break up?
Weight.
Yeah. Friction is in the negative I hat direction, so we don't have to break that up. Y is in the positive J, we don't need to break that up. Weight gets broken up, the exact same thing that we just did. And so our diagram becomes, we have W sine theta down the ramp, W cosine theta into the ramp, normal force out of the ramp, away from the ramp, and then we have kinetic friction up the ramp. Equations.
W sine theta minus
All right. And then our J equation.
y minus w cosine equal to
Times 0.
Yeah. Oh, yeah, that's 0.
And again, technically it's mass times 0, or you can just jump to straight 0 there. Those are the two equations. S, substitution. For what do we have a formula?
mg.
For weight. All right, so we have mg sine theta minus, we do have a formula for kinetic friction.
That's,
Coefficient of kinetic
Wow.
friction times the normal force.
Yep.
yeah.
UKY is equal to mass times acceleration, and then y is equal to mg cosine theta. We're solving for acceleration here. Normal force does play a factor here, so we have this plugging in for the normal force. So we now have mg sine theta minus uk mg cosine theta is equal to mass times acceleration.
Oh.
Can we simplify it?
Cancel out mass.
Yeah. Every term has a mass as a factor. And so with friction, the acceleration would be g sine theta minus uk g cosine theta. Oops. And you can leave it like that or factor the g out if you want. So let's use some numbers here.
Yes.
So let's make it, the mass doesn't matter, so we'll make it a gajillion kilograms.
Okay.
G, we're on some strange planet, the acceleration due to gravity is 9.8 meters per second squared.
Oh.
UK is 0.3, and theta will make 30 degrees. And so now it's a plug and chug. 9.8 times the sine of 30 degrees minus 0.3 times 9.8 times the cosine of 30 degrees. So that's 4.9 minus. The final answer, or the intermediate?
that number.
2.55?
Which is 2.35.
Yeah.
Yeah.
Oh. Well, it's like acceleration, so meters second
That's
squared.
right. Units, that'll get your points off.
Yes, it will. All right, so 2.35 meters per second squared. Questions to hear? Because we're about to add a complication. All right.
We're down.
All right, so no longer make the assumption that it will slide. We have mu sub s is equal to 0.7. And by the way, the coefficients of friction, I've never actually seen one bigger than 1. I don't know if there's any theoretical reason why it couldn't be. But,
So that's the maximum value for it before it slips, right?
right, we need to figure out, is the force down the ramp enough to overcome the maximum static? So the only thing that changes in our force diagram is we don't know, we have to assume that it's static to start with.
Slightly odd question. Is Velcro tension or is it static friction?
Tension, right? Is there like little parts?
I've never seen coefficient of friction chart that included Velcro. It is officially tension because it's a hook and loop type situation.
But there's also friction with it, with the hook actually, being to the loop.
You could probably come
Force
up
it.
with a muse.
I was just curious what we would think of it in the class, that's all.
Yeah, I've never seen any academic treatment with Velcro.
Okay.
So when solving a problem where you don't know if it's sliding or not, the first thing you need to do is you assume it is static. So the only thing that changes, because we did not plug numbers in until the end, it's simple enough just to put in u sub s. And this changes to 0.7.
Why don't we change that to 0.7?
Because we don't know if it's sliding or not, so first we have to do is establish, is it sliding? And so I have a mu sub s of 0.7 here, so we assume we're at the maximum static to see if we overcome it.
5.94.
So we get negative 1.04 meters per second squared. So therefore, the acceleration of the box is
Great enough to overcome the static friction?
Not great.
Oh, yeah, no, it isn't great enough.
No, it's not. I thought you said negative. How much would it have to be to overcome it? 0.7 meters per second squared?
Wait, how much would it have
Or
to?
would it have to just be positive? Oh, no, that's the, that right there is the acceleration of the box.
If we're at the maximum static.
If we're at the maximum static.
So it's not moving.
No, it is not.
So therefore, the acceleration is
Zero.
Now, some students have gone into a problem like this and they just took a gamble. Let's just assume it's sliding, they work through as if it's sliding already without checking to see if it's not sliding or not. This one, if I'm wading through the weeds as I'm trying to figure out what they did, whether I'll catch it or not. But you do need to check first, is it moving? If this actually worked, real answer here, that means that if we put a box on the ramp and it accelerates in the negative direction, we put a box on the ramp and suddenly it's accelerating up the ramp.
That would be quite a phenomenon.
That would be,
That's called an escalator.
we
We'd be in a world where.
Scientists everywhere are baffled.
Because wouldn't that, I mean, it's just like having a room with negative friction. Something's bad gonna happen.
kind of like the rocks in the desert that move around mysteriously, although they solved that, but.
Yeah, because it floods, right?
No,
Or is
it's,
it wind?
it's something about the ice that forms on the bottom of it that causes it to
slowly
sort of-
moves. Yeah, the ice moves it. Yeah, I remember that. It floods and then freezes and the ice moves it.
I like
Looks like
that.
it's sliding.
All right, so
Yes.
I think we can do the book sliding up the ramp problem.
Oh, good.
Any questions on this before we do book sliding up the ramp problem?
I don't think that's a question.
Most of them?
In the original problem, this was a coffee cup, and that was a book. The initial is 10 meters per second up the ramp. Coefficient of static friction is 0.4, coefficient of kinetic friction is 0.3. Book and cup. So the question is, how far up the ramp will the book slide? Oh, I need to give an angle here. Let's make this 50 degrees. How far up the ramp will the book slide? And will the book slide back down? We have two masses that we care about here, the book and the cup. It is an ideal string and ideal pulley. So we're not worried about the string is massless and stretchless and frictionless. Or if there is any stretch on the rope, it's at its maximum stretch, it's not going to stretch anymore. All right, so now what we really care about is the book and the cup, but since we're all sort of new in the process, let's just throw in we've got the four major pieces. Let's do the force diagram. So the force diagram.
Gravity pulled down on box C.
Say it again.
Gravity on box C going down and then going back.
What's the name of the force?
Oh, weight, yeah.
All right, so I have W sub C here. Oh, I forgot to throw in the earth.
You can throw in the earth? Oh.
Just grab your packet.
All right. One force, one pair of forces down.
Same
What else?
thing on the next one, box B, you go ahead and do that one.
All right, so W sub B and W sub D.
Then you have, force normal going that direction on that last box you leveled.
On the box.
Yeah. And you're gonna have it coming up off the ground as well.
Going which way on the ground?
It's,
Oh, wait,
it's the
sorry,
same
it's
angle.
gonna be going down.
But down.
Down.
Not down, it'll be going at an
Same.
angle.
That's what I mean.
Okay.
Oh, wait,
When you do the pair of forces, they're always in opposite directions.
The tension.
oh yeah, because that's the ramp, yeah.
Yes.
Okay, yeah, I forgot about the ramp. Yeah, okay, so, yeah, same thing on the other one.
Normal force here?
Yeah, so you're gonna have,
No, because it's
It's
off the
gonna-
ramp.
oh no, it's floating.
It's off the ramp.
It's not floating, it's attached to a rope.
Yeah, that's all, but it's off the ramp, yeah.
Yeah, so there's no normal force acting on the cup.
You have force of tension. going
So we do have
straight up
tension.
from
Which
the
way is
cup.
tension acting on the cup?
Straight up, towards the
Oh.
rope.
I hope so. If it's acting down, that means not only is it falling, but it's falling faster than the acceleration of gravity because you have something else pushing it.
Yeah.
There's gotta be something holding it up.
You have the rope going down,
I'll go with the spirit of what I think you mean,
yeah, going towards the box,
And
see,
then the tension on both.
or the cup.
oh, the cup, yeah.
Yeah. I guess box C works also in terms of context, but all right. So oh, by the way, we had the two small objects there, so we've got the gravitational forces done. We have only two things. We still have another normal force, actually.
You still got tension.
We got another tension too.
Yeah, we got a box.
All right, so I heard string normal force, so it's gonna be somewhere in that direction-ish. So Y sub R, Y sub R. So our normal forces are done.
Tension on the box, the top box.
Box into the rope and rope into the box. Right?
Let's speak it clearly.
So the
Force on the box.
force on the box goes towards the rope.
Okay,
The force on the rope goes towards the box.
now because this is an ideal rope, those two tensions at the ends of the rope are equal to each other in magnitude. When we do the complex force diagram, you can put these with a subscript and these with a different subscript, and that's fine. But for this, in order to solve it, we do need to acknowledge that those tensions are the same. So tension done.
I do not see another either.
Friction on the.
Well,
top
you got it on the box.
We do have
B
friction.
is going down, so it's gonna be going, yeah, no? it should be
No,
going
friction's
down.
going up.
Yes, for friction.
If it's going down, it should be going the
It's
opposite.
going down.
Steven?
You're going up.
The box is already moving up the ramp.
I thought the box was going down the ramp.
That's what,
Oh,
the
sorry,
book,
yeah.
sorry, thank you. The book is
Okay,
moving
well,
up the ramp
if
already.
it's going up, then yeah, it's still
So
going down.
friction's going
But
down.
however, on the ramp, then it'll be the direction I was talking about.
Yes.
Yeah, no.
So this is our friction is kinetic to start with.
Guess I need to read the problem a little more closely.
We're reading my mind. Just stay away from the dark areas.
That was the most fun.
Yeah, but doesn't necessarily help
Stay
here.
away, Madison, I was there.
Okay.
Just give myself minor, that's fine.
All right, so these are the two objects for which we will do a force diagram. What is the direction of the acceleration of the book?
Same as the,
Oh, it is down
So,
the ramp.
down.
It is down the ramp.
Acceleration will indeed be down the ramp. There are no forces acting up the ramp. There cannot be an acceleration up the ramp. The acceleration is down the ramp. It's slowing down, so the velocity and acceleration are opposite signs. So my acceleration is this way. And what about for the cup? Which way is the acceleration?
It should be downward as well.
All right, so when we choose our coordinate system, you can choose one of the axes to be in the direction of acceleration, or in this particular case, you could choose in the direction of movement. Both are acceptable here. It all depends on whether you want A to be positive or negative. So, up the ramp positive or down the ramp positive?
Up the ramp positive.
So there's I can call it IB hat and then JB hat. And the cup, since that is the positive direction, then we'll make this the positive direction also. And I'll just call this JC hat. Or IC hat, either one doesn't matter. We could have another direction here. It could have an I hat for the cup, but there are no forces in that direction, so you would just end up with an equation of 0 equals 0. It is true, but not helpful.
Thanks, but no thanks.
All right, so how many equations of motion will we have?
3.
Yes, 2 for that, 1 for that. All right, so we did the force diagram, we did the direction of acceleration, we did the coordinate axes. Decomposition, do we need to break anything up?
We need to do weight.
Yep, it's the only one.
Yeah.
So we have the cup here with its WC and FT. And then our box, we have FK down the ramp, FT down the ramp, and then we'll have a WB sine theta down the ramp, WB cosine theta into the ramp, and normal force that way. Make sure that's right, so I had 4 forces there, broke 1 up, so I have 5 here, okay, I'm good. So decomposition, done. So we'll have 3 equations, so I have I sub B hat, J sub B hat, and then J sub C hat. F equals MA as our model.
Get started with the I sub B.
Okay.
So we're gonna be adding W sub B cos theta.
You said I sub B? I sub B is up the ramp.
I sub B is
So it's negative f of t, negative f minus f of k minus w cos or sine theta. Equals ma.
All right, because we did not stick a negative sign in front of here, I'm expecting the acceleration to be a negative number. But that's fine, to me that makes more sense. You could put a negative here if you wanted to force acceleration to be a positive number, but acceleration as it stands here will be a negative number. All right, the J hat B,
now it's the y minus WB cos theta. equals.
NA. Oh yeah, 0. Whoops.
And JC,
We have force of tension.
FT minus WC.
WC, yeah.
Equals
Equals
zero.
no,
No,
not 0.
NA.
oh yeah, and then,
All right, there's a mistake here. What's wrong?
Our mistake.
It's an easy fix, but don't feel like you have to suddenly erase a lot of stuff. But there is a very crucial mistake here.
I don't see any differentiation between the F sub T and the F sub T between the.
Oh, we don't need that, because it is the same tension, same tension on both ends, because it's ideal.
Is that not 0?
Pardon?
Is that not 0?
No, because the cup is gonna be slowing down along with the book.
Was it supposed to be, is that 0?
That's 0.
Is that right?
Yeah, that is right.
Instead of going ahead and writing MG, we put down M.
Oh no, there's different directions of acceleration.
No, that's not an issue.
Oh, well, I tried.
It's still the same magnitude of acceleration regardless of different
Oh,
directions.
yeah.
I don't know, I just, you write F in place of MA because it equals it.
Must be
Oh,
something.
you know, we'll fix it in another.
Must be something.
All right, so, what do we have an equation?
Well, we have our kinetic friction.
Okay, so I got negative Ft minus mu k y minus, well, we have weight also, m g sine theta equals ma, y minus m g cosine theta, minus y equals m g cosine theta, and Ft minus mg equals ma. I just expanded the problem. We're almost to the point where we can't overlook the problem.
Is it that we're assuming the box is moving?
We are assuming the box is moving.
Okay.
Well, it's stated in the problem that it's moving.
You mean the book, I guess?
Say it again?
The book, you mean?
Yes, book. That other B word. It's a book about boxes, so I get confused.